All right, at a factory that produces doorknobs, we're back in 15.1. 1,500 have been produced. To check the quality, a random sample, so 1,500 have been produced, a random sample of 100 is selected to test for defects. Of the 100, 2 were found to be defective. Based on these results, what is the best estimate you can give for the number of defective doorknobs among the 1,500? Solve it 3 ways. Okay, I actually need more space than what I've got here, so I'm going to make this smaller. Okay, so what do we know here? Let's do the first method. Let's think about it as bins. So I've got 100 doorknobs, and they're going to go into a bin each. So they're going to go into 100 bins, 1 doorknob a bin. And remember that 2 are defective. So I'm going to have 2 defective bins of those 100. All right, and so I'm going to divide those 1,500 knobs. So I've got 100 bins. I need to put those 1,500 knobs into those 100 bins. And I need to see kind of how they fit. So I need to divide this by 100 so I can see how many of these go into each of those bins. So 1,500 divided by 100 is going to give me 15 knobs here. 1,500 divided by 100 is going to give me 15 knobs. So I'm going to put 15 knobs in each bin. So if I've got 100 bins, and that's getting 15, that's getting 15, that's getting 15, I know that there's going to be 2 bins that are defective. So 2 of these bins are going to be defective. So how many are defective? 30 are going to be defective. All right, let's do another method. All right, I know that 2 out of the 100 are defective. What is that as a decimal? 2 out of 100 is 0.02, which is 2%. So 2% of those 1,500 are going to be defective. So that could be, I could do this 2 over 100 times 1,500, or I could do 0.02 times 1,500. Either way, I'm going to get 30. Okay, let's think about another method. So, all right, let's do a proportion, defective to total. I know it's 2 over 100 is equal to, we don't know how many defective, to the total of 1,500. So I can do this a couple different ways. I could say, all right, 100 to 1,500 is times 15, so x equals 30. I could do it another way. Remember, we learned external, internal. I could say 100 to get to 2, I need to divide by 50. So I need to divide this by 50. And when I divide 1,500 by 50, what do you think I get? I get x equals 30. So there is 3 different ways to think about this problem. Let's do another one. At a light bulb factory, oops, sorry about that. At a light bulb factory, 1728 light bulbs are ready to be packaged. A worker randomly pulls 60 out and tests each one, and 2 are defective. All right, I'm going to make this smaller. All right, so what do we know here? We've got 1728 total, 60, and 2 are defective. Based on the information, what is the best estimate for the number of defective light bulbs among the 68? Well, I personally prefer the proportion method, so that's what I'm going to use. But you can use any method, defective to total. I know that 2 out of the 60 are defective in the sample, and I want to know how many are defective over that total. So I know to get from 60 to 2, I'm going to divide by 30. So I'm going to divide this guy by 30, and I get x equals, so 1728 divided by 30 gives me 57.6. So I'm going to say about 58. I'm going to round that up. If the light bulbs are put in boxes with 144 light bulbs in each, 12 packages of 12, how many defective light bulbs would you expect to find in a box? Well, let's think about it in the same way as a proportion. It's the defective to the total. That's what we're still asking. We're just changing the total. We know that 2 out of 60 are defective. So how many out of that 144 will be defective? Well, I can do the same thing. I know that this needs to be divided by 30, so this needs to be divided by 30. So x equals 144 divided by 30 is 4.8, so we would say about 5. That's kind of a lot, in my opinion, of defective light bulbs in a package. Now, this next example is different and a little challenging, so we're going to take it nice and slow. And I've got additional drawings here just to help us make sense of this because this can be challenging. So there is a bowl containing 80 green tiles and an unknown number of purple. So I'm just going to draw the bowl. And I've got 80 green tiles, 80 of those, and I've got an unknown amount of purple tiles. I take a random sample of 10 tiles and I find that 6 are green, 4 are green, and 6 are purple. So 1, 2, 3, 4, 5, 6 are purple, and 4 are green. Write at least 2 different expressions, A times B, for the number of purple tiles you predict there are based on the random sample, where A and B are numbers derived from 80, 10, 4, and 6. Okay, we're going to do this 3 different ways, and we're going to do them with math drawing. So let's just first make sense of this. Our sample is 10, and before, the difference is we've known the total. But in this case, we don't know the total. We don't know the total number of tiles, okay? We only know the relationship between green and purple in a sample. We know that out of 10 tiles, we've got 4 green and 6 purple, but we don't know, we know that there's 80 green and we don't know how many purple there are, okay? And so maybe you're already having an idea, you already know, just based on that alone, you can kind of make sense of it. But let's go through this here. So they want us to actually write an expression, not solve it. So if we go back here, you might have said, oh, you did it. This would be times 20. So this would be times 20. I know that there's 120 purple, and you'd be correct. But they actually want us to write different expressions for A times B. So this is a proportion. This is not an expression A times B. So we need to find a way to express this as 2 numbers multiplied by each other and explain how that works. So let's go through this piece by piece. Okay, so if we have our 80 green tiles and we divide those into groups, okay, and each group has 4 tiles, all right, because remember, we're allowed to use the numbers 80, 10, 4, and 6. So we've got our 80, and we're going to divide those into groups where each group had 4 tiles. So 80, we're going to put 4, 4, okay, 4, 4, 4, 4, 4, and we're going to keep doing that. We would have 80 over 4 groups, which makes sense, however many times we could do that. And then since we predict that each group with 4 green has to come with 6 purple, every time there was 4 green, there's got to be 6 purple with it every time we do that. And so then we would have the expression 80 over 4 groups times the 6 total purple, and that is our first expression. Let's think of it another way. All right, assume that every 4 green tiles has 6 purples to match with it every time. So every time we take the first 4 green tiles and we put them into 4 piles, 1 in each pile. So here we've got 1, 2, 3, 4 piles, 1 in each pile. Then we would take 6 purples and put them in 6 piles, just like that. 1, 2, 3, 4, 5, 6. And then we would do it again with the next 10. And then we would just kind of keep making sure that the green go with the green, purple go with, and we would keep going until we run out of tiles. This is the same as taking 8 tiles, 80, and dividing it into 4 equal groups, because we've got 80 green and we're putting them into 1, 2, 3, 4 groups. So 80 over 4 is the number of tiles in each group, because we're going to do that 80 out of 4 times. Remember, we only have 80 green, so we're going to do that 80 over 4 times. And there are 6 groups of equal size that have purple tiles, so we have 6 times 80 over 4 purple tiles. One more time here. If we assume that the ratio of 6 purple to 4 green is the whole representative of the whole bowl, and we know we have 80 green and unknown purple, then we can imagine then the entire 80 green are being represented with 4 blocks, whereas because there's 4 green tiles. Whereas the entire purple would be represented in 6 blocks because there are 6 purple. The amount of each block represents 1 tile, or 1/4 because they're blocks of the green. Then, since the purple amount is represented with 6 blocks and each block represents 1/4 of the 80, then the purple is 6/4 of the 80. So, one of these you try is similar to that one that we just did, and the other one is similar to the previous 2. Take your time here and then press play when you're ready to see the solutions. And then go ahead and complete this You Explore. We're going to cover capture, recapture, and then press play when you're ready to do our final example together. So we're going to continue looking at the capture, recapture, which is what you did in the previous exploration. A researcher wants to estimate the number of rabbits in a region, and they catch 30. And after those are tagged, they release them unharmed. A few days later, they set traps, and this time they catch 35. And of those 35, 5 are tagged, which indicates that they had been trapped a few days earlier. Based on these results, what is the best estimate you can give for the number of rabbits in the region? Okay, so let's look at this 2 different ways. They say 3, so we're going to look at 3 different ways. First way, we've got tagged to total. We know that of the 35 trapped, 5 are tagged. So this is the sample that is tagged. This is the sample that's tagged. All right, and that is the population should have the exact same ratio, right? So we know what's 5 over 35, that's 1 over 7. So we know that 1 over 7, how many were actually tagged? 30 were tagged. So if 1 over 7 is equal to 30, they make up 1/7 of the population. So the total population would be 30 times 7, or 210. And don't worry if that didn't resonate. We'll do it a couple different ways. All right, so for every 35 tagged, for every 35 caught, 5 will be tagged. And we could keep doing that, and we know 30 are tagged. So let's keep going. We know that 30 are tagged. So 5, 10, 15, 20, 25, 30. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. So how many is that? We know that 30 are tagged. So how many in the total population, if we add all those up, or 35 times 6, we get 210. And let's look at one other way here. We can use a proportion, tag over total. We know that we've got 5 over 35 tagged, and we know that in the total population, we originally tagged 30, but we don't know how many there are total. Well, we know 5 to 35, we multiply by 7, 210. And finally here, why is randomness important? Randomness is really important so that we can make sure things are effective and that things are safe. So when we're talking about experiments in a drug trial, it's important that, we're keeping things safe. So I encourage you to read here about double-blind and controlled studies here, and that concludes section 15.1.